days. Yeah, and the 6th of June is also is a Monday. That is also a public holiday. That you not wonder why there is nothing happens. So, and for my lecture, we are good in time because we have now a lot of sensors. And for the sensors, many of the sensors, when you see the temperature sensors also, that is very easy to understand. You have it in your script. I hope everybody has downloaded the script, and you can read these sensors. I must not explain every sensor in detail, so that you can read it. And if you have questions, you can also ask. The next Monday, you can ask when you have questions regarding the sensors. But the most are very, very simple, and therefore I must not explain it and skip some of the sensors so that you read it at home. For the examination, we have a time for the examination. Let me have a look. But you should also have it in the OSCAR system. Let me have a look. We have the examination on the 28th of June. The time I have not here, I must look in the internet, but you should have it in the examination timetable. But on the 28th of June, we have the examination. And for the examination is very important, the first part of the lecture. Therefore, the first part, I have skipped nothing because that is the most important part. It is sure that one task will be the task about the calculation of the calibration coefficients. The line approximation, how to fill in, or what calibration coefficient you have to fill into the software. The software you get from me, but you have to fill in the numbers, you have to calculate the numbers, and so on. That is a very important point, and it is sure that from this area you have to calculate something. Otherwise, will be also some questions in a kind of multiple choice, where I have a question and then 3, 4 possible answers where you can say what is right and what is wrong. So, and now we make some points at the sensors where I think that it is not so easy to understand that I do, but the very easy sensors you should read in your script. And I start with the measurement of elongation and from this resulting quantities. And the main keyword is strain gauges. Strain gauges we have in metal, and we have it in semiconductor strain gauges. But the most important are still the metal strain gauges, because they are very easy to manufacture, and we can use it, let me say extremely good, because they have all the same temperature coefficient. The temperature coefficient is a very important parameter. We will see how it works and that the temperature coefficient plays a very important role. The semiconductor strain gauges we cannot produce with exactly the same temperature coefficient, and therefore to use semiconductor strain gauges is only possible if you have a completely electronic around where you can measure the influence of the temperature to every strain gauge. Therefore, the semiconductor strain gauges are normally part of a very complex electronic system. But the metal strain gauges are not so sensitive, but we have today amplifier. And you see here the principle, you have the strain gauge and you elongate it a little bit, this delta of the length, and you see the metal will be longer, and because the volumina is constant, it must be smaller. And when we look for the formula, the resistance is the specific resistance multiplied with L, with the length divided by the area. You see here, the length will be longer and the area here will be smaller. Both leads to a higher resistance when you elongate, and when you compress, the resistance will be lower. The problem is the specific resistance, because the specific resistance is temperature depending. When you heat up the wire, you change the specific resistance, and with this you change also the resistance of the strain gauge. And therefore we have to eliminate the influence of the temperature. And that do we so that we set the strain gauges in a full bridge. A half bridge would be also possible, but in practice normally you use every time the full bridge, because you have then also the higher sensitivity. But now, when you see the full bridge, when you heat up R1 and R2, both are going or increase the resistance, but on both sides of the bridge. And therefore, the voltage in the diagonal voltage will not change, because when both resistance going up or down, you have every time the same voltage in the diagonal. But when you increase one and decrease the other, then you get a change of the voltage. And therefore, this R1 is on top of your body. That is a form body what you have. And R2 is under the form body. And when you let in or lead in this force, you get a very small elongation on this side and a small compression on the other side. So that this resistance R1 would be bigger, that would increase. R4, this is this one, would be smaller. And this voltage would going down. On the other side, I would like that the voltage is going up, that you have a maximum on diagonal voltage. That means R3 has to be increase and R2 has to be decrease. Therefore, R3 is on top. When you set the force in, you have an elongation for R3, and you have a compression for R4. So that this voltage is going up, and you have then the diagonal voltage. And the diagonal voltage is only depending from the so-called form factor. That means these two are longer, these two are shorter, but the temperature has the same influence to all the strain gauges. And in a bridge, when all strain gauges going up, you have from this influence no influence. From this temperature, that for example, the strain gauges increasing all in the same way. Therefore, it is eliminated. But therefore, every strain gauge has to have exactly the same temperature coefficient. And that is the case when you have metal strain gauges. That is not the case when you have semiconductor strain gauges. And therefore, semiconductor strain gauges you cannot use in this easy way. And therefore, many devices today are working with these metal strain gauges. When you buy a balance, for example, with an electronic display, in a balance, normally we have these metal strain gauges. But for example, when you have measurement devices for blood pressure, this is a huge market. Every hospital has thousands of measurement devices for blood pressure. There are developed electronics under the use of semiconductor strain gauges, but that must be a mass production so that it is efficient to use a high developed electronic to measure the temperature and also the temperature coefficient on each semiconductor strain gauges. The normality is this. So, and I would like to show you how to calculate the delta of the resistance. When I look for this formula, that is the same as here, only that we have replaced the area by P multiplied with the diameter powered by 2 divided by 4, but divided by 4, the 4 comes on top. That means this 4p d powered by 2 is the same as the area. And when I now calculate the delta R and divide by R so that I have the relatively change of the resistance, I can use this formula. And what I can use is a propagation for systematic error, but that means also systematic influences. Therefore, as we have had it in the beginning of the lecture, the systematic propagation of systematic errors, I have told you that this has not an importance regarding the